So in the laboratory, you have been exposed now to probably some of the qualitative work that we can do with amino acids. So you've taken these amino acids and you've done these qualitative tests to them to figure out what they are, see what color they change, see what happens inside of the test tube, and identify an unknown. Well, there's actually a better, more systematic way in order to do that, and one of those is using the PI values of these amino acids. So how do we calculate this PI value that's kind of independent or very special, almost a fingerprint to every one of these amino acids that we will be studying? Well, the PI is very easy to describe, it's very easy to define, and it's very easy to calculate. So let's first start with the definition. So PI basically means isoelectric point. And this is the pH where there is no charge on the amino acid. Okay, now you got to be really careful with the wording here because it will say no charge, but no matter what you do to these amino acids, they will always have a charge. They will either be fully positive, fully negative, or they will be a Zwitter ion, carrying a positive and a negative both. And it all depends on what kind of acid environment that you put it in. So when we say no charge, it's a misnomer because we always will have a charge on these amino acids. What we should say here is no overall charge on the amino acid. Okay, so what that means is that if we take the template for an amino acid structure and it looks like this, well, we're seeing a positive charge here and a negative charge there. And if you add them together, you get no overall charge. They kind of cancel each other out, right? It's kind of like you made a deposit and you wrote a check on the same day, and your bank account is going to come out zero. So one part of the molecule has a positive, one part of the molecule has a negative, and the positive and the negative cancel each other out. That is what we say no overall charge. So the amino acids that we were dealing with, we gave you a rounded-about figure of the pKa's, right? We said that the COO minus group has a pKa of around 2, or the COOH group has a pKa of around 2, and then the pKa of the protonated amine is about 9.5, somewhere in that vicinity. But careful wording was used during that time, and I said these are averages. They could actually range. They could go below these values and they can go above these values. And I told you to take a look in your textbook. If you're working out of the 7th edition text, this is table 22.3. If you're working out of another version of the text, the table is still in there. You might just have to look for it a little bit, but you're going to see all of the amino acids that are listed, and you will see their exact pKa values for the carboxylic end and the amino end. Now, some of these amino acids, their R groups also have a pKa, because think about it. We went through some families of amino acids and we said that some of these were acidic in nature and some of these were basic in nature, and that included the NH2 groups, the amines and the amides. So we know that some of these can be protonated as far as their side chains go. And those pKa's for the side chains are also listed for you. So these are the numbers that we need in order to work out the PI values for the amino acids. So what does this table look like? Well, you can find that in the PowerPoint. The table is there. You can also find it in your textbook, like I mentioned just a few seconds ago. So this is what the table will begin to look like. They have listed all of the amino acids here on the left, and then they've given you a column with the actual pKa values for the COOH groups. Notice they all kind of target around 2, so some of them are a little bit above and some of them are a little bit below, but that's our average that we like to use. The pKa's for the NH3 groups Well, they're all listed here as well, and notice they're about 9.5, somewhere in that vicinity. Some of them are a little below, some of them are a little above. And then some of these amino acids, the acid and the base ones especially, they also have a pKa value for their side chain. So they probably have some kind of carboxylic acid, or they probably have some type of amine or amide group on them that can lose or gain a proton. And these have pKa values, and those are listed on the chart as well. So how do I calculate the pi, and what purpose is it for me to calculate a pi? You know, what's the big deal here? Well, to calculate the pi value, again, the pH, where this amino acid will have a neutral charge. That is what we are after. Okay, to calculate it, you basically take the 2 pi is equal to pKa1 plus pKa2, and then you take the average. So you're going to take those two numbers and you're going to divide by 2. So you're going to really simply average the pKa values. That is what we're after. Okay, so let's do an example. I'll show you how easy these examples are going to be. So let's take a look at maybe an example that says calculate the pi for alanine. Okay, so I'm given the task to calculate the isoelectric point, the pH where alanine is completely neutral, no net charge at all, meaning the species that carry the positive charge and the species that carries the negative charge, well, they kind of cancel each other out. This is the pH where those charges completely neutralize. Okay, so how do we do it? Well, I go to that table and I need to find alanine. So if we go to this table and I find alanine, they've done a nice cute little job because they've put it in alphabetical order for you, so that way it's easier to find. So alanine is up here at the very top, and we see that the pKa value for COOH is actually 2.34. So let me draw the structure for alanine first. Okay, so alanine is a carbon that has a carboxylic acid, and it has this NH3, this protonated amine, and a hydrogen, and a CH3 group. All right. So this COOH group has a pKa of 2.34. That came straight from the chart. Now, if I look on that same chart and find the pKa for the NH3 group, this is 9.69. So 9.69. So I'm given the task to calculate the pi value. I just take those two numbers and I get an average. That's all that I do. So I'll take 9.69 and I'll add 2.34 to it, and then I divide by 2. It's as simple as that. It can't really get any harder at all. So 9.69 plus 2.34 gives you 12.03, and then I'm going to divide by 2, and this gives me a pi of 6.02. We'll round it to 2 sig figs after the decimal. 2 after here, 2 after there, we'll keep 2 after here. And this is what I would call the isoelectric point. So all amino acids will have their own isoelectric points, and that is how you calculate the isoelectric point for them. Okay, so use the chart. You don't have to memorize these tables. You don't have to memorize these numbers. Take a look at these amino acids and figure out how to calculate the pi values. It's as simple as this. Now, the only complication that can exist, the only complication that you probably will see, is what if they give you one of these amino acids that have 3 pKa's? Do you average all 3? And the answer is quickly no. You do not do all 3. So let's look at aspartic acid. Okay, so aspartic acid. If I didn't call it aspartic acid, well, that probably means at physiological pH it's not an acid. Aspartic acid is aspartate, so let's draw the structure for aspartate. This is NH3 plus, and then the carbon, and then the hydrogen, and then the COO minus, and then down here below was a CH2 with a COO minus as well. Okay, so this is one of those acidic amino acids that we had in the bunch. And if you look at the pKa values for aspartic acid, you will see that the pKa of the COOH group in that table, well, if you find it, it's 2.09. And then you'll see the pKa value for the amino group for aspartic acid, and this is 9.82. And then you'll also see a third column that's listed, and it will say pKa of the side chain. Well, this is the side chain. This is the R group. That's what that represents. So this has a proton that can get lost. It's an acid, so it will probably be on the low end. And sure enough, it is. This is 3.86. Okay, so how do I calculate the pI of something like aspartic acid or aspartate? You do not, and I repeat, you do not take all three of these values and average them. That is not what you do. What you do is you take a look at your choices that are given to you on the sheet of paper, and here they are, and you take the ones that are the closest in value, and you average only those two. So you still average only 2 points. You only consider 2 points, and that is it. So you look at these 2 points and you take the ones that are closest in value. So that means 2.09 and 3.86 are closer together than this 9.82. 3.86 and 9.82, they're really far apart from each other. 9.82 and 2.09, they're even further apart from each other. So you take your two closest values, and that is what you average. So I'll take 2.09 plus 3.86, and then I'll divide that by 2. So 2.09 and 3.86, that is 5.95, and then I'll divide that by 2, and I'll get 2.98 as the pI value. So that is how you will treat the ones that do have this third pKa value. So the pIs of most amino acids that have these ionizable side chains, that's kind of what we call those, you take the average of the pKa values of the ionizing groups that are closest in value. That's how you do them every single time. So if you take a look at lysine, lysine has 3 pKa's, 2.18, 8.95, and 10.79. You take the two that are closest together, so that means 10.79 and 8.95, and then you will take the average of that value, and that average is the pI for that amino acid. So what's the big story with pI values? You know, why do we want to learn how to calculate them? Why are they important? We'll see in the next video. So stay tuned. There's more to pI than what meets the eye, and we'll come back and we'll talk about how we can put pI to use for us.